Okay, so let's look at this generator here then. If you look at it then, it looks very much like your motor setup. And what we've got here is we've got a vertically positioned coil. Now this is actually attached to slip rings rather than that split ring commutator. So the split ring one would have given you positive DC EMF and current all the time. This one's going to give us AC. So you can see in this slip ring one, you'll find that one of the wires is always connected to the orange terminal here, or the orange ring if you like, slip ring, and the green one is always connected to the other one. So that allows us to actually go negative and positive, you'll find. So let's have a look at this. So if you start this off, at the moment we've got the brushes there and the slip rings. If you rotate this through here, at the moment it's in a vertical position. You'll find the magnetic flux change here that's going on is the rate is very slow at the moment in this position here. In fact, it's zero. So you'll find you're on zero current. When you actually get it rotating then, so it rotates through a certain angle, it'll cut through a certain amount of flux and induce a certain EMF, and this case it's about a half size current there. If you rotate it further though, you go up to your full size current when it's in this position here. And that's when the rate of change of flux is at the greatest. Okay. Now if you continue on here, normally if you had the split ring then, this would have actually switched over brushes with terminals and you would have generated positive current again. But I haven't got that, I've got a slip ring here. And if you do that, this time it's going to go negative here. Okay. And it goes even bigger negative after that. So this is how you sort of get an AC current generated by using the slip ring effect here from a simple generator. But we're going from we're going from kinetic energy here into electrical energy using it as a generator. Okay, so let's have a look at that here. So what you should see here is this current being induced as it goes through the rotation process. So in one half of the motion you get your positive EMF, your positive current here, and the other half you're going to get your negative one there. So this will generate alternating current. Okay, so all we need to do in the power station then is get a way of actually rotating these coils so that she goes through this process using the slip rings to generate positive and then negative in this nice sine wave curve here. We could use either steam generated by coal-fired power stations or by gas. We could use hydroelectricity in terms of water falling down a hill, turning some turbines that will turn this. Or we could actually use wind power, which would do the same sort of thing. Or we could use nuclear power, where the nuclear energy is used to turn water to steam to drive these turbines. So just be aware of that alternating generator there. It's quite a difficult thing to draw and actually describe, so we'll go through that again later on. So once it's done that, we need to actually sort of bear in mind that the power station gives you a certain amount of voltage here. So if you look at your typical power station, for example in South Australia, that actually generates 11,000 volts at the coils, where the coils are being turned past those magnets in the generators. Okay? So from there they actually go through a step-up transformer that we're going to look at today, and they go up to 330,000 volts, so they're transmitted at a much higher voltage to travel those long distances. Okay. Now, when it does that, and then it's got to arrive at the right places, it's got to be stepped down again through a transformer process, so that at the house you end up with the 240 volts that you currently use. So the reason you have to sort of step this up and down is to do with this power equals voltage times by intensity of current. So it turns out if you want to reduce your power losses due to heating up of the wires, you want to really use a low current down those wires over those long distances. Now to do that, to transmit the same amount of power, you have to boost your voltage in turn. So if you want to get this successfully transmitted long distances, you keep the current low to reduce your losses due to heat energy there in the wires. So to do that you need to step it up while it's actually travelling the long distances, and at the end you step it down for domestic use. Okay, so that's something to keep in mind. Now how does this work? Well, don't forget we've already worked out that if you push a magnet into a coil of wire, you will actually induce an EMF in that wire. So what I've got here is an arrangement here, the sort of typical one you'll get in a transformer then. So they've got an iron core there, I've done it as a square shape here. It's laminated, in other words there's layers of insulation in between it to reduce the eddy currents you'd normally get generated down there by the coil changing its magnetic flux. So just bear that in mind. So what you have here is two coils. You've got a primary coil where you actually sort of put the EMF into to start with, and then you've got a secondary coil. So if you imagine this being connected to just a simple switch to start with, a DC, and it's turned on, when you actually sort of turn this on, you're going to get a current through here. You'll get a magnetic field generated along that iron centre, if you like, that iron core. And that will move past this secondary coil and change the flux link with that coil, and therefore induce an EMF and a current in the secondary coil. So we're talking primary school here, secondary school. It starts here in the primary and it's going to the secondary. Okay, so let's just switch it on once. Now of course, once you switch it on once and it goes stable, the flux goes stable, and that would go to 0 again. So what they do instead is we generate this with AC using an AC generator, a slip ring one, so that this actual current, if you like, keeps going backwards and forwards, growing in one direction and then growing in the other direction and reversing, okay? So that will actually cause the field here to grow out and then grow back again, and grow out and back again, always moving through that secondary coil here. And that will induce an EMF in the secondary coil and a current, okay? So the idea is obviously with the transformer is to try and transform it from one voltage type to another. In the case here, we want to go from small to large. So how does it do that? Well, it turns out if we actually use the relationship here between the number of coils and the voltage, if you compare the voltage in the primary coil and the voltage in the secondary one, the determining factor here is how many coils do I have in the first one and how many do I have in the secondary one. Okay, so if you look at that then, if we got this particular drawing, I think it's got 6 in the primary one there, and it's got 12 if you count them in the secondary one. So the ratio here of primary to secondary voltage here should be 1 to 2. In other words, if I was to start with 1000 volts here in the primary coil, I would expect to end up with 2000 volts induced in the other side here. All right there? Because I've got twice as many coils in the secondary one, I should get twice the voltage. So it's a very simple proportionality relationship. If your primary one to your secondary one was, say, 10 coils to 200, it's going to go up by 20 times. The voltage will go up by 20 times. So this is the formula on the formula sheet to use for that. And basically you normally get the 3 of these and get asked to work out the other one. Okay. Now just a couple other things to consider here. Some people will say then, therefore, if I'm getting more voltage out, I'm obviously gaining energy here. But something to bear in mind is that its power equals V times I. So if I go and do this over here somewhere, sign there, power equals V times I. So what you'll find happening is, when you actually get an increase in the voltage, say it goes to twice the voltage, you'll find the current drops by even amount. So the overall power from one to the other stays the same. All right, so you might get more voltage, but you'll get less current coming out of that wire there, this secondary coil here. Just thought I'd show you some pictures here. Some of the substations you might see around the place to actually convert voltage, you might see in some of the locations, and obviously there's some that actually convert it at the starts of streets in some cases before they go into your home. So there's quite a few step down ones that they do before they get into your house. So I just thought I'd point that out. Now what I've got here is an example of the generator here. We're just going to turn some coils of wire there through the actual magnetic field that's there. And if I've got this set on DC to start with, you'll find that it actually is switching between those half brushes there here, and you might be able to see that half brush there. There's a gap just here, and that would actually cause it to give you that DC output where it's always in the same direction there. Alright, that's the DC output. Okay. I'm using an LED here though. And if you actually switch this over to an AC one, it doesn't look much difference, but believe me, you actually got a different set of rings here. You've got a set of slip rings here where this one's always connected to one of the rings and that one's always to the other. So just sort of show you that to finish off. Okay, thank you.